It's a pleasure to welcome one of our alumni back to IIS. Zohar, you will tell us about quantum numbers. And as always, we'll go to dinner. Everybody's welcome. And if you're interested, please send me an email right after the seminar so I can get a head count, take a reservation.
Thank you very much. It's great to be back. I haven't been back since COVID, since the pandemic. So many things have changed, I noticed. Thanks again. Today I'll tell you a story that I've been interested in the last couple of years. So there are some papers with Gabriel Cuomo, who is in the audience, with Siwei Zhang, and some upcoming ideas and some previous papers that I'll be referring to. And also, just obviously interrupt me with any questions at any point. So the main concept that we'll try to explore today in some very simple examples is the idea that the ground states of quantum systems at large quantum numbers, they have some interesting weakly coupled descriptions. So there is some, even if the underlying microscopic theory is very strongly coupled in the vacuum, when you go to when you investigate ground states which have many particles or large spin or large charge density, typically there is a new notion of an h bar like parameter, which could be very small in favorable circumstances. And then there is a weakly coupled description. It's sometimes possible to guess the weakly coupled description and then make some contact with interesting actual systems and so on. So this is the underlying idea. I do not know how generally true this idea is, but it is true in many, many, many examples. Perhaps in all the examples that I'm familiar with. Okay. Now a closely related problem, which the first half of this talk will be dedicated to, is the problem of understanding the scaling dimensions of operators in some conformal field theories. Thanks to the operator state correspondence, the scaling dimensions of local operators are related to energy eigenstates. In some scaling dimensions of local operators are related to energy eigenstates on the sphere. And sometimes I'll refer to the sphere as a trap, because then in the second half of the talk, there will be some other spaces in which the quantum system will be placed, in which there will be some kind of trap. There will be some potential that traps the particles. So I'll sometimes refer to the sphere as a particular example of a trap. So the problem of understanding scaling dimensions of local operators in a conformal field theory is not dissimilar from the problem of understanding the ground states of quantum systems at large quantum numbers. So this will be the context of the first part. So let me just give you the outline. I'll first review what do we know about the scaling dimensions of local operators with large spin. So this maps to some ground state of the quantum system with large momentum or large spin, and I'll review what's known about it. There was a lot of work on this subject in the last decade and a lot of progress. Then I'll start a slightly new subject, which is a spinning but also charged ground states. And this introduces conceptually new difficulties having to do with some emergent chirality and degeneracy that I'll explain. And then we'll make a guess for an effective field theory describing local operators with charge and spin. This effective field theory is quite exotic. It has weird approximate infinite symmetries, infinite degeneracies, and so on. We will analyze this effective field theory. And then finally, I'll apply these ideas to non-relativistic systems of dilute gases, dilute Bose gases, and we'll make some comparison with experiments. So surprisingly, the predictions of this part seem to match pretty closely with already existing experiments. But of course, it can be improved. So this is the outline. So first, I'll start with reviewing what is known about the following problem. In the conformal field theory, we have local operators of spin J and scaling dimension delta to set the notation. And a very canonical question you can ask is, what is the minimal possible scaling dimension of a primary operator with a spin j, where j is very large. Let's say j is 100 or 1,000. So this via radial quantization is the same as trying to find the ground state on the sphere of a quantum system which has some given momentum on the sphere. So this is a very canonical problem that you can ask pretty much in every conformal filter in 2+1, 3+1 dimensions. So this is the answer. Now I'm going to tell you the answer and then I'll explain the answer. I'm not going to derive the answer today. So the answer is that the answer is that it turns out that operators in conformal filters sit on some rigid trajectories. So meaning that their scaling dimension is linear in the spin. So by rigid trajectory, I just mean the delta is approximately linear in the spin, very much reminiscent of the linearity of m squared in j in for confining hadrons. So here we have a scaling dimension that's linear in j up to very small corrections. And a lot is known about the small corrections. We know the exponents, we even know the coefficients in favorable examples. And then there is an order 1 contribution from the primaries O1 and O2. So the claim is that you can start from any two composite operators, O1, O2. Then you can stick J derivatives in a very particular way so that this whole thing is a primary. And the scaling dimension of this huge composite operator that's made out of the partons in quotation marks, O1 and O2 is linear in J, and it receives an additive contribution from O1 and O2. And if you want to imagine what is the state on this trap, on the sphere, you can think about it as two swirling particles. Two particles that are swirling relativistically around each other in an antipodal fashion. So they're placed antipodally on the sphere, and they're swirling very fast. Okay, and there's been a lot of work fixing these corrections and so on. So this is the answer for the yes?
For any O1 and O2, you can make states like that for
Yes.
large J.
Yes.
But is it the case that all large J states arise this way for some O1 and O2?
Yes. It's sufficiently large J, all the states are of this form.
Even in 2 dimensions?
No, 1+1 is very different.
Okay.
This is true only in 2+1 and 3+1 dimensions and above. The arguments that prove these assertions have an assumption that there is a gap in the twist, so that there are no operators of vanishing twist, where twist is delta minus J. So there is a loophole in 1+1, but following this work, people have fixed this loophole, and also there are concrete statements in 1+1. But this is generally true in 2+1 and 3+1 dimensions. So in particular, you may say that ADS-CFT suggests that high spin states are black holes. But of course, this is not true. The true ground state at very high spin is not a black hole. It's essentially this operator. It's just that you didn't reach high enough spin. So spinning black holes have instabilities, which are called superradiance instabilities, and eventually they decay to these kind of states. Okay, so this is the story for any conformal filter. Let me just show you that this is proof from data. So this is data for the Wilson-Fisher fixed point in 3.99 dimensions. This is the O1 model, so the Ising model in 3.99 dimensions. You see very beautiful rigid trajectories. This is the main trajectory. There are also daughter trajectories, very much like in the physics of partons. I will soon explain that to get daughter trajectories, you can insert additional things here, such as the box, the box operator, the Laplacian. It doesn't lead to any additional spin, but it raises the scaling dimension by some additional additive factors here. It leads to daughter trajectories.
Yeah. So how do we tell this kind of operator is not black hole, like from boundary? How do you tell?
It has a very small degeneracy. You see from these rigid trajectories, this is another one. There is no degeneracy.
Oh, okay.
This is like unique. The ground state essentially has entropy 0. Okay. So this is the leading trajectory, and then there are daughter trajectories with higher twist. So this is some data from the Wilson-Fisher fixed points. Much more impressive is, of course, the numerical data from the bootstrap. This is a plot that I shamelessly stole from Simon's Dublin. This is numerical bootstrap, but here I'm plotting delta minus J. and this is J, and you see that it just goes to a constant, exactly like Regge theory predicts. And what is this constant? It's 1.04. Yes,
So this means that black holes are not primary?
black holes are not the true ground state at high enough spin.
Oh, okay.
They have super radiant instabilities and they decay. What is this constant 1.04? Let's look at the formula. It's the sum of the constituents. And in this case, for the Ising model, the partons are the fundamental spin field, which has scaling dimension 0.52. So 0.52 times 2, that's the asymptote. Okay, so we see a very beautiful approach to the Regge physics with pretty large deviations for small spin operators. Okay, we have a very nice Regge trajectory. Okay. So even if the underlying conformal field here is very strongly coupled, the story that I told you so far is completely universal. And the corrections in 1/j or 1/j squared can be computed. So the lore in the field is that there is asymptotic freedom at small angles. So even if the theory is strongly coupled, the large spin sector is completely solvable. You can think about it as the theory, as if the theory becomes free at very small angles in quotation marks. And also, what is the state in the trap? In the trap interpretation, this formula that delta has slope 1 is of course nothing but the statement that the energy goes like momentum, which is the dispersion relation of relativistic particles. So it's just a boosted excitation. And that's why I gave you this picture of two antipodal particles moving at a high velocity on the sphere. Okay. So this is the story for spin. Are there any questions about spin? Now I'll show you a generalization of this question, which leads to many interesting puzzles. Okay, no more questions. So now I'll consider a model where there is also particle number symmetry or a U1 symmetry. It's going, so just to keep something concrete in mind, think about the O2 Wilson-Fisher model, but any other theory with a U1 symmetry would be equally good to discuss. So we have an elementary, well, I still use the word field, I meant operator. We have an elementary operator O of x or phi of x, which has charge 1 and scaling dimension like 0.52 in the O2 model. And you can ask the following question. What are the charged Regge trajectories? Regge trajectories that carry charge q. So you can compose, you can using this idea that the spin, that large spin operators are built by this construction from before, we can construct charge q large spin operators in the following way. Q doesn't have to be large. Q could be 5, 7. So we have, let's say, q copies of the operator phi, and then we insert derivatives as long as the sum of the insertions here adds up to j. So this gives you an operator whose scaling dimension you can reliably compute. It gives you, yeah.
How do we interpret this more complicated operator in terms of a bilinear with derivatives?
It's not so. The story about large spin operators is not limited to a bilinear construction. You can construct operators with any number of composites separated by many derivatives. As long as every two composite operators are separated by d with a large power, we have a good perturbation theory to compute the scaling dimension.
Then what would be the first term, the order 1? Would it be the sum of all these operators? Or?
Yes, the sum over all the contributions from the partons, and this you can think about as like the number of derivatives in sum. So there is an intuition for that Parisi taught me, which is that he said that maybe you can think about it as that this is like a Taylor expansion of an operator which is bilocal, OX and OY, and when they're very far away, this is like a term from the Taylor series, and maybe that's why the dimension is not renormalized, because it looks like the dimension is barely renormalized here. The small corrections, yeah, you can compute them, but it's very small. So every time two composites are separated by many derivatives, you can use that approximate freedom. Okay. So this construction therefore makes sense, and it gives you a charged Regge trajectory with spin j and charge q. But this leads to some interesting puzzles. So first of all, that's the scaling dimension. Yes.
Is it q plus one?
Oh, no. Yes, you caught me there, unfortunately. Yes, I'm sorry for that.
Just trying to understand.
Yeah, I'm sorry for that. Fair enough. So this is the scaling dimension of this charged Regge trajectory.
That's correct, see? Look what you wrote there, you put Q minus one.
Yeah, but now I have phi squared.
Ah.
So here I wanted to make a comment that there are many other operators with the same charge and the same spin. This is another construction where you have phi squared and then q minus one phi's, and you insert some derivatives so that the spin adds up to J. This would be subleading in the Regge sense because the scaling dimension of phi squared is more than twice than the scaling dimension of phi. So this parton is pretty heavy. So this is some subleading Regge trajectory. And the picture on the sphere for this funny charged Regge trajectories, instead of two particles swirling around each other, you have now q particles swirling around each other. So what's so interesting about that? The interesting thing is that we encounter a huge approximate degeneracy already on the leading Regge trajectory. That's because when we wrote this formula, we didn't say how we spread out, how we distribute the derivatives. As long as all the j's are large, I can distribute the derivatives in any way I want. And it will not change the scaling dimension to leading order. So you encounter a huge approximate degeneracy, which goes like q log j. That's the first thing, that we must be able to understand what happens to the degeneracy. And the second thing is that you encounter a notion of chirality. Because if we look at this formula again, we see that d plus adds 1 unit of angular momentum and also 1 unit of scaling dimension. But if I added a d minus somewhere, it would reduce the angular momentum while increasing the scaling dimension. And therefore it would lie on a subleading Regge trajectory. So d plus keeps you on the same Regge trajectory while d minus goes to the daughter trajectory. So we see that plus and minus are not on the same footing. If you think about this as the ground state or something. So we see some notion of chirality and we see a large entropy. And the question is, what is the fate of these two facts? So first of all, I have a slide which is quite technical, but I'll explain it quickly if there are questions about it. You can try to estimate using the large spin perturbation theory. So there is a whole technology that goes into computing these small corrections. You can try to compute these small corrections for discharged Regge trajectories and try to get some intuition of what's the fate of this approximate degeneracy and chirality. And what you get, I'll just summarize. The first thing that you can obtain is that you expect corrections at order q cubed over j. So as long as q is like order 1 and j is very large, the corrections are tiny, and our conclusion is the degeneracy is there, and it's split by a very small amount. The second thing is you can ask, what is the force between these partons? So you can think about these partons swirling on the sphere as free particles to first approximation. That's why the scaling dimension is not renormalized. But when you go to a higher order, like q cubed over j, you can ask, do they attract or do they repel? And this is a hard computation at one loop in this high spin effective theory. And it turns out that the attraction is 0.308, while the repulsion is 0.304. And so the attraction wins by a tiny amount. So in fact, these partons are a little bit attractive. They attract each other at first order. So all this goes to say that the corrections to this formula are slightly negative. And when q cubed over j becomes appreciable, they might be important.
Sorry,
Yeah.
I'm a bit confused about when you have phi squared and you say it's a subleading trajectory because I feel like you just that's the same as you just put a one derivative.
Yeah, but
j equal to 0.
Right.
Why
but
that
this-
is subleading?
But the idea that you add the dimensions of these phi's and j's is only true when there are many derivatives.
Oh,
Of course, there is huge renormalization when you go from phi to phi, from phi squared to twice phi.
okay.
So the scaling dimension of phi squared is much larger than twice the scaling dimension of phi. But if they're separated by many derivatives, there is no renormalization. The scaling dimension behaves classically.
That only happens when delta is large.
when J is large.
When J is.
That's why there is a good, when you're at like large quantum numbers, the effective quantum corrections become small. That's the idea. Okay. But you also see it in the rigid trajectories, that for the first few operators, there's pretty large renormalization, but then it goes away. Okay. So there's slight attraction, and therefore the scaling dimension is slightly smaller than the free scaling dimension. You could say that it's weird that gravity, like that in the ADS, in an ADS language, we have partons swirling the center of ADS. They enjoy electric repulsion because they're charged, but they also enjoy gravitational attraction. And in this model, the gravitational attraction wins. So gravity is certainly not the weakest force in this sense. And there are more examples in this paper of that phenomenon. I don't know what it means for the weak gravity conjecture, but it's certainly not true in this case, that gravity loses. Okay. So these are some initial comments, and now let me make the next step. So the question is really what happens when the J becomes of order Q squared, because you remember the corrections were of order Q cubed over J. So when Q squared becomes of order J, these corrections become important, partons attract, and the idea is that we get some condensation. So the whole talk will be about some weird classical solution that we found, which has a remarkable similarity to discharge rigid trajectories, reproducing the entropy, reproducing the chirality, and it's observable in the lab. So I'll now show you a classical solution, which is kind of continuously connected to this swirling partons picture. And it reproduces the same properties.
You said the attraction was Q cubed over J,
Yes.
and you're comparing that to, I think you would compare it to J.
No, you have to compare it to this. Let me show you. It's a great comment, by the way. We spent hours.
But you want to compare it to Q.
Yes, you have to compare it to Q, which is the mass of the partons.
J is bigger than Q, right?
Yes. But as soon as this term is dominated by some small corrections, you cannot trust this formula anymore. So something new happens.
Okay, so you're just saying, when does it become comparable to one of those two terms? You're not saying it, when does it become dominant?
Solution has the exact same Regis law. We'll
Okay,
find a
okay.
classical
Yeah, yeah.
solution where this term is exactly the same. So our classical solution will have the exact same Regis law. It will have slightly different subleading corrections.
Yeah.
But
Thanks.
we have chirality and entropy and all these properties as before.
Sorry, so you're interested in J of order Q?
No, J is big compared to Q. When you do, right?
So
What's the limit you take in J?
there is nothing wrong with anything I said as long as J is the biggest parameter. Now, when Q becomes of, large enough, this description breaks down because they start attracting each other.
Yeah.
And I'm now going to find, the idea of our work was that when Q is large enough, this clump of particles actually becomes a condensate. You see this in the picture.
Does that follow from what you said before? Because
No.
if Q is large,
Yes.
then there are more. So which one is larger, Q or J?
So the interesting physics begins when Q squared is of order J.
Okay, but that means that there are lots of operators and fewer derivatives.
Yes.
Okay, but that.
Oh, it's the other way around. You're
That's-
talking about Q is large and J is large, and J is bigger than,
They're both large.
right.
Yeah, but
But if
which
Q
one is
squared is of order J, then J is large.
So as long as Q is small, everything I said goes through without any issues, with tiny corrections. When Q squared becomes of order J, okay, when you crank up Q so that Q squared becomes of order J, I'm now going to propose a new picture for these states.
Okay, so Q is still much smaller than J.
Yes, but Q squared is of order J, but they're both large. So what is the point? The point is that the way we drew this picture is supposed to suggest that maybe due to the attraction of these particles, they will soon condense. And we will indeed now find a new classical solution with very interesting properties, reproducing everything I just said. So there is some kind of continuous transition, we believe. So let me just show you how it goes. Since we're guessing that the partons are going to condense, we will try to work with an action which has a single U1 Nambu-Goldstone bow, a single U1 Nambu-Goldstone boson. And you have to write an action for this U1 Goldstone boson which respects conformal symmetry. Because so the idea conceptually is that we have a state with some charge density and angular momentum, but still there is conformal symmetry. So the action has to respect conformal symmetry, because if you have a conformally invariant field theory, the word identities of conformal transformations are true in every state. And therefore the fluctuations have to obey conformal invariance in every state. So we have to write a conformally invariant action. It's just that we're going to expand the action around the non-trivial solution with spin and charge. So the action that respects conformal invariance for a single U1 Nambu-Goldstone boson in 2+1 dimensions is this thing. And unlike before, this is not a typo now. The cube is not a typo. That's what you need for the action to be conformally invariant. So particle number density is given by this formula. So we're going to expand around the state with a non-zero particle density and non-zero spin. And we'll just investigate the quantization, like the quantization of the fluctuations around that state.
What is meant by the absolute value of d chi? It makes sense in Euclidean signature, but.
It's also in Minkowski signature, so we take d chi squared as a Minkowski 3-vector squared, and then we take the absolute value. We assume it's a time like,
Okay.
yeah, because the evolution has to be
Sorry, how do the indices go?
d chi cubed. So it's really d mu chi to the power 3.
And the theory is only good when the argument is positive.
Yes. The field theory, the physics makes sense only when the argument is positive. Because this describes the evolution, the propagation of waves, condensed state of matter.
Chi is the phase, the Goldstone direction, right?
Yes.
So can't we expand around chi equals 0?
No, we need to have this is the particle density. So we expand around. So the usual story, if you just have a state with a particle density, no angular momentum, we expand around a solution that looks like some chemical potential plus fluctuations. This is necessary to set the background density of particles. Now we'll find this is the ordinary classical solution that people have investigated since Bogolubov to describe small waves of a superfluid. We found a new solution which describes this swirling at these condensed particles with angular momentum. So that's what I'm going to explain now.
I'm very confused. What are the symmetries that you import? You assume U1 and the conformal symmetry.
Yes.
And then you're only interested in expanding around this.
This is the old story. This is just describes a state with constant particle density and no momentum. I'm going to expand around a different solution. I'm going to tell you which one soon.
And is the solution you're going to expand around, will it be conformally invariant or not?
No, it breaks the conformal symmetry spontaneously.
And then shouldn't you include other terms?
No.
Okay.
Why would I?
Because you're expanding around something that doesn't preserve conformal symmetry.
It's a spontaneously broken. It's just a state of the underlying CFT. And we're assuming that the small fluctuations of the full CFT in that state are the same as the small fluctuations of this theory in that state. Right? I'm not saying that the CFT is equal to this weird model. That of course wouldn't make sense. You cannot quantize this model around small particle number states. The statement is that the small fluctuations of this model around some new classical solution are the same as the fluctuations of the full CFT around this state with the particles. But you must impose conformal symmetry, yes. Otherwise, you won't even get, like, you know that, for instance, the states of the CFT around some have to have descendants. So you won't get these things unless you impose conformal invariance.
So there should be another classical solution obtained by acting with the symmetries in your classical solution.
Yeah, I'll dedicate a whole slide to showing you that.
Okay.
You'll see that there are special phonons, which if you add them to the solution, they correspond to a conformal transformation of the solution. Some protected phonons. This will be an important consistency check. So I'm just saying here that this action is the same as saying that the equation of state of conformal matter in 2+1 dimensions is that the pressure is equal to the chemical potential cube, because the chemical potential is this thing. And of course, this action has been used recently in many other papers for lots of applications. I can talk about it later. So we found a new solution, which I'm just drawing in the picture. I'm not going to write the full classical solution. So the new solution, this is the sphere. So it's a solution on the sphere, which is our trap. So there is no superfluid here. This is an empty gap phase. There is spinning superfluid in the red region, and the green region is a boundary layer. It's a boundary between the superfluid and the empty phase. The boundary layer has this size, q to the power 3/2 over j. And this is the energy of this solution. Yeah.
Those arrows you drew aren't showing the boundary layer, they're showing the thickness of the whole superfluid strip.
Okay, so this is the whole superfluid strip.
Okay,
This arrow says that the green piece is a boundary layer between the superfluid and the empty phase.
Yeah, yeah.
Okay, and this is the full energy.
thickness of the boundary layer is
Q to the power 3/2 over j.
same as the,
No, so that was Q cubed over j. This is Q to the power 3/2 over j. Okay,
so the twiddle next to it doesn't refer to that blue arrow, blue double-headed arrow?
the twiddle says that this is the thickness of the superfluid region,
Yeah,
and it's Q to the power 3/2 over j.
yeah. And is the boundary layer thinner?
Oh, much thinner, much smaller. Parametrically smaller. I didn't even write how small it
Okay,
is.
okay.
The boundary layer is really small, and we
We
analyze
don't
it in
care how,
detail.
we don't
It's
care
very
how thin it
important
is.
for subleading corrections and quantization. We analyze it in great detail, but it's
Yeah, okay,
not in
thanks.
this talk. It's very technical and it's subtle.
But is your effective field theory good in the blue region? The empty region?
No, the empty region is gap. So we model it by boundary conditions. So we have a superfluid that's swirling in some region with boundary
But
conditions.
that's likely to be not completely universal. Different systems might favor different boundary conditions.
No,
You think there's a universal?
yes, we proved that there is a universal answer. So there is the following theorem. If you have a region with superfluid and empty outside, the only consistent boundary condition is Neumann. If particle number is conserved, you can impose only Neumann up to small operators that you can add on the boundary, and these operators are subleading. They don't change the leading order predictions. So superfluid theory has a unique boundary condition, as long as particle number is conserved. That was actually proven in a paper before by Gabriel and collaborators. Okay, so this is the energy of this configuration. The claim to fame is that it has an exactly linear term in J. It's a classical solution where the energy scales like J, so it reproduces the Regis slope. And the corrections are exactly of the same order that I told you before, Q cubed over J.
What is C?
C is the stiffness coefficient of the superfluid. So it's a parameter in the effective action that we cannot guess. It's a Wilson coefficient that depends on the model. So I'm saying things about the O2 model where I know C from numerical simulations, but in other field theories with U1, that number will be different. It's always a positive number. Okay. Okay. So when is this solution interesting? As I said, it's interesting when J is of order Q squared, but you can take J to be even smaller. This solution still makes sense. So there is some window of a parameter space where this is the answer to the problem of the charge red trajectories and the symmetries. This solution breaks spontaneously conformal symmetries, but it preserves the particle number, and it preserves time translations. Sorry, it preserves it breaks spontaneously particle number in some conformal symmetries, but it preserves time translations and rotations. The solution is clearly the rotation invariant, and it also preserves energy. Okay, so this is a solution, but let's talk a little bit about the fluctuations. This is where the story deviates a lot from what was known about superfluid theory. So as I said, first claim to fame is that it has exactly linear Regis slope, so it matches the Parton picture, and there are small corrections. But when you analyze the small fluctuations around the superfluid, you encounter something wildly different from the ordinary theory of phonons around superfluids. Let me just remind you that in the usual story of a superfluid, there are small fluctuations in the density, which move with a dispersion relation that looks like that. So the frequency is the absolute value of the momentum, and this is the speed of sound. That's how every superfluid behaves at low energies due to the Goldstone theorem. Here, we find this bizarre effective action, which has only a minus derivative, where minus is the direction of the swirling. And so this is the leading order. This is the leading order theory of phonons around the superfluid. It's a non-standard quadratic theory. It's not d minus d plus, it's d minus pi squared. Okay, and the quantization of this theory is very subtle. It also has bizarre symmetries. So that's what I'm going to explain next. Are there any questions about what I'm doing?
Are there higher order corrections involve the other derivatives?
Yes, there will be corrections. I'll describe them. This is the leading term by far numerically. So first of all, what are the symmetries of this weird action? There is this symmetry where you essentially do an arbitrary conformal transformation in the x plus direction. There is another symmetry that looks like a U1 where you shift x minus by an arbitrary function of x plus. Finally, you can shift the fluctuation field by an arbitrary function of x plus. I think the last one is more like a fractonic symmetry. Maybe I'm using the wrong language, but it looks similar to some symmetries that appear in the literature on fractons. And the first two symmetries, they are SL2 times U1, and they appeared in the Kerr-CFT correspondence. I don't know for what reason, but they appeared also in the Kerr-CFT correspondence, the exact same algebra of symmetries. And the dispersion relation differs substantially from the one of superfluids because we don't have an absolute value. So the frequency is exactly is 1/r, which is the radius of the sphere, the trap, times the momentum, but there is no absolute value. And this leads to very exotic consequences.
Wait,
Yes,
but N is,
n is the angular momentum, is the momentum of the equator.
it can be negative?
Yes. So n can be positive or negative. And the frequency is the momentum along the.
Does that mean there's negative energy?
There are modes with
Lower,
negative.
you're not expanding around the ground state?
Well, I fixed the momentum, right? We're expanding around the
Right,
state
yeah.
with fixed momentum.
True, yeah.
So the modes which lower the energy.
Momentum will
they
lower the
also Lower
energy.
the momentum.
So there's
In fact, you expect such
Yeah,
modes.
right, okay.
You
yeah.
should expect that there will be ways to lower the momentum, but these modes cannot be excited because you have momentum conservation. So once you spin the superfluid, then you just let it go. These modes cannot be excited anymore. But there are other modes that can be excited, and that's the main point. Any sum of integers, which is 0, has the same quantum numbers as the vacuum. And it has the same energy as the vacuum. So this model has infinite degeneracy. Infinite energy degeneracy, exactly like in our description.
So if you include the higher order derivatives, won't they lift this degeneracy?
They will. I'll even compute them soon. But this is the leading order answer. What does it describe like in pictures? We have swirling superfluid, but its shape, which I assume to be exactly circular, can fluctuate. And what this means, this degeneracy of the vacuum, where you take any set of integers which sums to 0, and therefore it has the same quantum numbers as the vacuum, it means that you could actually change the shape of that swirling strip to anything you want. And the shape will be time independent and just swirl together with the superfluid. So it's infinite degeneracy, and these shape deformations are not mobile. They just move together with the superfluid. Okay, so this is the physical point.
It's rigid rotations.
Rigid rotations. But the density is a function, is a non-trivial function here, but once you deform the shape, the wave doesn't propagate. It just moves together with the superfluid. It looks a little bit, I mean, people who work on this JT gravity have some similar pictures for the deform. But anyway, this is much more down to earth. So you have arbitrary shape deformations that move together with the superfluid, and they're exactly degenerate with the vacuum, infinite degeneracy. Now I turn to Nati's question. That there must be some corrections to this picture. It cannot be exact.
When you consider the sum over different ni to be 0, but give you each ni, that means you have one configuration of this kind of.
So each ni by itself is a mode which would change the total momentum.
Yeah.
I don't want to do that. The thing you want to do is to fix the momentum and the particle density, and then look at excitations. So you must only look at excitations that have 0 momentum.
Yeah, but
0 additional momentum, I mean.
okay.
You see what I'm saying? Or
Yeah. Okay. Maybe I just want to kind of visualize like you have different ni. How does it change the shape of the?
yeah, every ni has like n nodes.
Oh, okay.
So this would be like maybe the mode 3 and -3. So So this would maybe correspond to 3 plus minus 3.
I see, I see.
So the integers you would take as like 3 and minus 3, something like that.
So if J is finite, say 23 or something, do you merely mean infinite degeneracy, or is that some power of
Infinite
J?
degeneracy is just a property of this field theory. This field theory looks sick, but it's actually
It's a property of the field theory, which corresponds to some sense of the limit of large J.
You'll be cut off zone and corrections.
Okay, so large state limit.
This field theory looks sick, but it's actually completely fine.
Yeah.
It just describes the system that it describes what I just said. That there's an infinite degeneracy, and you can actually easily split it. So here's the first correction. These coefficients are not random. It's a toil to compute them. You have to compute them starting from the microscopic description. So delta, what is delta? Let me remind you. Delta is this small parameter that appeared here. It's just numerically small in the whole window where this description makes sense. So there is a small correction which involves both plus and minus derivatives. In the experiment that I'll soon compare to, this is 10 to the minus 4. It's really a small correction, but it changes the dispersion relation for modes that are moving left from modes that are moving right in such a way that if you're fast, you can see in your brain that now the degeneracy is lifted, because every sum of integers that adds up to 0 will now have a slightly bigger frequency than 0. And the gap becomes delta squared over R. So it changes the dispersion relation in this peculiar way. This correction. It only affects the n smaller than 0 modes, not the n bigger than 0 modes. Okay, so this is the more precise dispersion relation. Again, I'm saying in experiment, this is 10 to the minus 4, tiny effect, but it's measurable. And it leads to the degeneracy. And here's the answer to Nari's question. I was a little quick with something. I only told you about the dynamics of modes which depend on this angle on the equator. I didn't tell you much about the radial modes. There are also excitations that don't move in the equator, but they're like radial excitations. I don't have time to explain them, but if you combine some special radial excitations and some very special angular excitations, there are exactly 3 modes which have protected dispersion relation, and they lead to the action of the conformal symmetry. So when you add them to the superfluid, they correspond to an infinitesimal rotation of the configuration that we found by broken rotations and blah, blah.
So I'm confused about the directions. Is it rotation such that D class is non-trivial, is non-zero, or D minus?
So you see that every solution has to have D minus pi vanishing. So
So D plus can be arbitrarily big.
so the functions that you can shift your fluctuation by are any function of x plus.
So I can add to this terms which depend on many derivatives. Choose whether it's plus or minus without costing me a lot of energy.
Yes,
So
maybe, but I think I'm afraid they will be redundant because D minus squared pi is 0. I'm afraid they might be redundant. If you don't have plus derivatives, I'm afraid it will be redundant. You see, this operator is not redundant.
yes, but you can multiply it by arbitrary powers. Also D
D
minus
minus
pi.
pi, yes.
The D arbitrary power of D minus pi.
Yes.
They should be equally relevant. They should say equally significant.
No,
not
they will be, no, they will be very small for small fluctuations. Because you're looking at small fluctuations of a classical solution. So pi is small.
No, but it's maybe D minus to the 10th times pi. Is this suppressed?
Yes, because D minus squared is 0 by the equations of motion.
The whole thing is rotating. So it has either P minus or P plus classically. Is it P plus or P minus? It has
You-
by rotating.
I
There's a
understand what
number
you're
which is
saying.
non-zero.
Yes, I understand, but that number is just, we computed that number. If you just add functions which are non-zero on the classical solution, it's all absorbed here. When we computed this, we computed the effect on the small fluctuations already. This was not it's not, you see what I'm saying?
No,
You're asking what is the energy of a small fluctuation of your solution?
Right.
That's what we computed.
no, but I'm asking about the large fluctuation, which would also not cost you a lot of energy.
Okay, those we have not computed, but I believe they are just given by conformal transformation. We just computed small fluctuations, and indeed we found 3 fluctuations which have protected dispersion. They correspond to rotating the solution. I believe that other fluctuations that cost you no energy will be just exponentiations of this.
Why three instead of, I can see two.
It's because I couldn't draw a, yes, you can see two.
Because there's an axis about which it's rotating, and that's two numbers.
These are the broken rotational symmetries. There are more protected excitations. So if you go back to the description in terms of conformal filtering, if you have a primary operator, you can hit it with three types of derivatives to make a descendant: d minus, d plus, and d transverse. So there should be three protected.
Have a classical description, the three modes, in terms of the picture with the stripe.
I think it does. It's like a conformal transformation on S2 times R, if I'm not mistaken.
It's not just a rotation. It's
I don't think so.
I think this question is a cousin of mine.
It's not just a rotation, it's a conformal transformation.
yeah, okay.
I think that his question is a cousin of mine. Because I would guess that there are all these symmetries that you draw.
Yeah.
So you should introduce collective coordinates for them. And
Uh,
because because you might be formed by a lot in a continuous fashion, it shouldn't cost you a lot of energy.
Right. I agree.
So the effective action that you should be using should include these collective coordinates.
Right. On the other hand, what we're doing is that we are throwing away the collective coordinates and we're looking at small fluctuations, which are genuine small fluctuations modulo the zero modes. And that's what I'm describing. The collective coordinates correspond to some operations which are captured by just adding these phonons in some cases, or just rotating the whole thing, so they're less non-trivial. So the dispersion relation that I brought in particular, you see that I omitted n equals 0. N equals 0 is another important zero mode that changes the total charge of the superfluid. So I omitted everything that has to do with the zero modes. Okay, let me just quickly summarize before I go to the second part. We reproduced the Regis flow. We found some weird effective filtering. And there is some small corrections that lead to the infinite symmetries and degeneracy. Now, let me show you how this connects to actual experiments in nonrelativistic systems. So we did so far I just told you some story about the superfluid on a sphere and some relativistic conformal filtering and some Regis trajectories, but okay, clearly the same physics should be true in a trap. In an actual non-relativistic superfluid that's in a Bose-Einstein condensate phase in a trap, and you start spinning it. So it's known from experiments already from 20 years ago that when you start spinning the superfluid, vortices appear. This is called the abrikosov lattice. There is a lattice of vortices. That's very nice and interesting. But much more recently, people started looking at much faster rotation. So when you start rotating this bucket in a faster fashion, and then they indeed saw that the hole opens up. And the hole looks a lot like this giant vortex that I described before. Because now inside there is nothing. It's a gapped phase. There is no superfluid. And there is some superfluid moving on a ring. So the idea is that when you start spinning a superfluid, when you go to high enough frequencies, you eventually settle in this phase, which is the supersonic giant vortex. And this was actually recently done not just in Monte Carlo, but in an actual experiment. And amazingly enough, when people looked at the fluctuations, these are shaped fluctuations of this giant vortex, they see modes which move almost together with the superfluid. So there is already very nice evidence for chiral modes that are co-rotating with the superfluid. These are these shaped modes, and it looks exactly like our prediction. It's a little bit preliminary to say that it verifies the prediction, because we don't know yet that this is really in the giant vortex phase. There's some work to be done, but it looks very, very close.
You know if they're using an anharmonic trap or?
Yes.
Yeah, they have to, right? Because otherwise it would.
Yeah. If it's only a quadratic trap, it would just.
They have a steeper trap.
Yeah, you need to put a trap, otherwise it spills out.
Yeah, and harmonic isn't the trap.
Anharmonic is enough. Anharmonic is enough.
Okay.
Sorry, what am I pointing at?
Yeah, you say anharmonic there, which
Yes.
yeah, part of the fourth, yeah. Part of
Yeah,
the fourth.
you must have an anharmonic
Yeah, I see
trap,
it, like
and it's
part of the
here.
fourth. Yeah, yeah, yeah. Thanks.
Otherwise, it spills out. But I think.
And they did that in the experiment.
That's all correct, yeah.
Yeah, thanks.
So there, it's already very, so you see the shape here. So this is like a L=2 wave where the shape was deformed with two nodes. And it seems to be moving with the superfluid coherently with almost zero frequency. So it looks very promising. Now, you can you can repeat the exercise of computing the dispersion relation, the effective field theory in this model. It's just a non-relativistic version of what I told you before. You can do it in several setups. One is the Gross-Pitevsky model, which is actually what I'm going to focus on. And it's not a very difficult exercise. I'll spare you the details since I'm almost running out of time. And I'll just tell you the idea. So the idea is that you want to find the new solution of the superfluid, which is localized to some annulus, like in this experiment, with some width, which we'll call delta, in accordance with our previous notation. And the size of the trap is R. So you want to find the new solution and look at the fluctuations. That's what we did. We found a new solution. We looked at the fluctuations. Here, the outer boundary, because it's a hard trap. I'm just showing you the solution for a hard trap. You can also do it for the anharmonic trap. It's in the paper. But for the hard trap, it's the inner boundary that can fluctuate. And these are chiral modes that have infinite degeneracy and they move coherently with the superfluid. It seems that they're what they're saying in experiment. And these are the dispersion relation. So this upper formula is a dispersion relation that includes some radial modes. I haven't talked about the radial modes. While this formula is the more interesting ones, which have a trivial radial profile, and they just spin coherently with the superfluid and lead to infinite degeneracy. So indeed, you see that the linear term is n. There is no absolute value. It's the same physics as before. And then there is a tiny correction, which is down by delta over r, where delta is the width of the annulus and r is the radius of the annulus. You can see from the experiment that it's very small. So these corrections are indeed tiny in experiments. In already existing experiments, the annulus is very narrow. And so we computed explicitly the small corrections. Hopefully in the future it can be matched to experiment. Okay, so this parameter here depends on the exact trap, on the exact equation of state and so on. I'll leave the details for the paper if you're interested. The idea is the same as what I explained before. So there are some small differences from the relativistic case in the way the expansion organizes itself, but it's basically similar. There are chiral modes, there is a very large degeneracy, large symmetries, and so on. So let me just now finally give you a summary. We found that there are chiral excitations in rotating superfluids. They have the same action as the chiral mode in the quantum Hall effect. They appear though for a completely different reason. It amazingly matches to the Regge of charged heavy operators. So there is very nice correspondence with the large spin expansion. We found an effective field theory with a very large degeneracy and a very small gap. There are small corrections that lift the infinite degeneracy. And here are some open questions. I haven't said anything about 3+1 dimensions. The whole analysis was in 2+1. And we actually didn't work out the 3+1 dimensional case. And of course, you can ask what is the ADS-CFT counterpart of this story. So in ADS-CFT, you have Q particles swirling around the center of ADS. They should experience gravitational attraction, which overcomes the Coulomb repulsion, as I mentioned before, and maybe fall into some boson star. So maybe what we're describing here is just a boson star in the language of the ADS-CFT correspondence. So could be that the state that is dual to this giant vortex is just a boson star, a spinning axion star. Okay. And finally, there are interesting questions about the superfluid theory itself. I mentioned that at the beginning you have this lattice of vortices and then you get this giant vortex, and it's actually not yet known what are the phases of these rotating superfluids. What are the phase transitions between the vortex lattice with a hole, or the giant vortex? Are these first order or second order transitions and so on? This is not yet known. Okay, so this is the end. Thank you so much.
Other question, so could we experimentally see the degeneracy?
Yeah, I think so. I think that's what it's a little preliminary, but I think that's what they kind of saw here.
Yeah.
Because you see they have frequency, they have modes with almost zero frequency. They have modes with very, very small frequency on top of the classical configuration.
Oh,
They just looked at this fluctuation and they measure its frequency. And they find that it's very small.
oh, yeah, but to check, you really have a large degeneracy, you have to check it all different.
Yes, it's just, yeah, just recent. We've been communicating with this Brook. Hopefully in the future it will be. This is from Pavon. I think it's from France. It's an experiment from France. Yeah.
So low frequency means that that oval doesn't rotate, or rotates very slowly.
It means that you start from a circle, that's the ground state, then you make it a little bit oval,
But that will be almost time independent.
and the oval will rotate in the same frequency as the original circle.
Oh, so that picture on the upper right is a snapshot of the oval, but if
Yes.
we watch it, it'll be spinning.
Yes, so yeah, that's exactly right. So the general picture is that we have these deformations of the shape, and they rotate with the superfluid. And they don't have otherwise any propagation. They just rotate rotate with the foot. It's like a rigid body. You just make it you deform the shape and it spins with the original frequency.
It's not like Lasso where the deformation seems to stand still.
No,
You know,
in the lasso, the deformation seems still if you look at it from below.
But relative to.
Here, the deformation is still relative to the original reference frame, which is spinning with the ground state. Let me show you again the dispersion relation. Maybe I missed this. I did not explain this point. Okay. This is the dispersion relation. Okay, what it describes is modes that move together with the original frequency of rotation. So you can make an arbitrary deformation of the shape, but it moves in the same frequency. You can also see it from the effective field theory. You can modify the shape by any function of x plus. That means that you have an arbitrary shape, but it moves at the speed of light. It's not static. In the lasso, the magic is that if you look at it from below, it looks static. Here it's the opposite. It's actually moving with the original superfluid.
So do you also have a phase transition as you lower the charge from superfluid to something that's not superfluid? Your original picture, your original picture was not sure what it meant, equally spaced partons or something.
Yeah, that's the large spin. We call it the large spin. Sorry, we call it the large spin limit. But the particles are not condensed yet.
Right, so and that's a phase transition. If we go to large J and
We spent a lot of time trying to put it on the computer and find if it's a phase transition or no.
if you do large J,
We don't know we don't know if this condensation is the second order, first order. We don't know.
but is there a non-condensed phase?
Yes, this is the non-condensed phase. This large
There.
Yeah, it's like when you have 5 particles. If you have Q is 5.
Well, but let's say J is large and let's say, we take J to infinity and Q to infinity much slower than J.
Then I think it doesn't condense. That's my opinion.
You think it doesn't condense, so there should be a phase transition
Yeah,
there,
that's the.
but you don't need,
I think there is a phase transition when this happens.
so it goes from that to the giant vortex, to the vortex lattice with the hole, to the vortex lattice, and then after the vortex lattice, if I increase the charge, what's it gonna do? Is that the last thing, or?
No, you have just homogeneous superfluid. Just a static homogeneous superfluid.
No, we're keeping J large.
Yeah, but that's
Keeping J large, increasing Q.
Okay, instead of a vortex lattice, you'll just have 2 vortices. 2 fundamental
No, but if
vortices.
J is large, the number of vortices is proportional to J, right?
Yeah, but remember that the angular momentum is the number of vortices times the number of particles. So even with just 2 vortices, you can have huge angular momentum.
Oh, so you're saying if I have large J and I keep increasing Q, it'll just go down to
Yeah, it will just become 2 vortices and that's it.
I see,
And
it's
that
not
will be
really,
the end of the
it'll
story.
never go to something.
At some point, the vortices will decay and the phonons will carry the angular momentum because also phonons can carry angular momentum.
Yeah,
Yeah, and that will be the end of the story. But all these other phases are known. This phase that I described today is new.
yeah, okay, thanks.
When you said that you tried to study the phase transition numerically, does that require picking a model?
Yes.
What was the model you used?
Gross-Pitesky.
that has this nonlinear term which describes some kind of short range repulsion or.
Yes. Exactly. I mean, it was just a vain attempt to try to understand the phases, but clearly this phase exists numerically, and it theoretically makes a lot of sense. It looks so similar to the large speed limit, so most likely it exists, but again, it has to be verified by experiment.
But doesn't Gross-Pitkowski basically already assume you have a condensate?
No, because you have to prove that you have to find the ground state of this nonlinear Schrödinger equation with fixed particle number and fixed angular momentum. Nobody said that the ground state has a large expectation value of the field operator.
Okay.
That's not guaranteed.
So you're doing quantum Gross-Pitkowski?
Yeah, quantum growth.
Okay, thank you.
Can I ask a question? So, if you just follow the leading red trajectory down to the red intercept, is there a universal behavior for that red intercept depending on the charge?
I don't know. I never tried that to go all the way to the intercept. I don't know the answer. It's too difficult. Maybe Gabriel knows. I really don't know. I never tried to go all the way to the intercept. It's like,
I'm still puzzled by what's the rationale behind this action with the 3/2? Is this the unique action satisfying some requirement? Is the.
and that's the unique, I claim this is the unique action for a single real field which transforms nonlinearly under U1 by shifts, and that is conformally invariant.
So why isn't that the exact answer if this is the unique?
Because this action only has one real field, so it cannot be expanded around the configurations with small numbers of particles. It's
But you can't have it both ways.
I meant unique. I didn't say I meant unique, but there are infinitely many Wilson coefficients with operators which have higher derivatives.
So unique with first derivatives only is probably.
Unique which has no acceleration terms.
Okay, so this is the unique.
So there are more operators that extremely complicated, like this part chi, this part chi, this go.
Yes, but they break the symmetry.
No, they're completely
You
invariant.
divide by power of d pi squared.
Yeah, and you need to divide it by powers of d pi to make them dimensionally correct. It's an it's an effective action that you can use without any worry in configurations where d chi is large. The absolute value of d chi is large. It's an effective. It's like, I don't know. It's like any effective filtering. It has a cutoff, which is the absolute value of d chi, and this is the leading term.
So we shouldn't think of it as, in the case when the symmetry is spontaneously broken, we think that there's some coset, we write a nonlinear sigma model in the coset. That's not.
That's exactly this. That's exactly the same thing. In pion physics, we have f pi, and we expand in 1 over f pi.
Right, but there's also a term with up to 2 derivatives, which includes the global part of the group, and then there are terms with 4 derivatives.
Yes.
Right.
So this is the analog of the 2 derivative term. If you want an analogy, it's the analog of that. It's the leading action that is compatible with the symmetries.
In 3 + 1, it would be this 4 derivative.
In 3 + 1, it will be power 4, which is called in mathematics, I forgot the name. There is a name to that weird operator. Forgot the name. He actually wrote a paper about it, I forgot the name. I wrote a paper. Panates. It's called the Panates operator in 3 + 1.
If there are no more questions, before we thank.
Thank you again.
I want to thank you for the nice shirt. And also remind you of dinner, if you're interested, please send me an email so that I take a reservation.